And let's see, need a keyboard. Will that do it?
Do you want the keyboard?
Well, let's see this. There we go. Okay.
All right. As promised, okay, we'll start with our scientific program, and it's the introduction to the particle model and perturbative QCD by Fred.
Hey, thank you. Welcome. We're glad you're all here. We didn't lose anybody so far, so that's a good sign. This is the first of two lectures giving you an overall introduction to the part-time model and perturbative QCD. And then throughout the school, you'll hear various details about this as folks go. So here it is. That's it. There's the QCD Lagrangian. Nice, very compact, fits very well. But if you don't know how to read that, it may look like a lot of Greek symbols. And it's a little bit like music to some extent. I'm an amateur musician. And so here is Mozart's inverted retrograde canon in G. And again, a bunch of dots. But if you don't know how to interpret that, it looks like a bunch of dots. But as you come to know the music better, you understand their patterns and symmetries. There's themes, melody, harmony, interaction, counterpoint, and structure. In particular, this one has a very neat feature that is rotationally invariant. So I just rotated by 180 degrees. And if you look closely, you'll see that's actually invariant. So Mozart in particular like to play games with that. And we're going to do something similar, looking for the symmetries and patterns inside QCD. So here we have the four fundamental forces. We've already unified electroweak and electromagnetism and weak interaction. But of the four, three of these are perturbative. So if you go out to large distances, they get weak, and you can do perturbation expansions. But the strong interaction, that's strong at large distances. But because of that, it's claimed QCD is our most perfect physical theory. Don't take my word for it. Frank Wilczek got the Nobel Prize for QCD. I pulled that from his paper. But he argues that in many respects, it's our most complex. It has asymptotic freedom, strong color confinement, and all the associated manifestations. But how complex can it be? It fits in a coffee cup. So there we go. We're going to dive into that. And it does a remarkable job. This is a bit dated plot, but you see as a function, for example, of PT over many decades, the data in theory are remarkable for a variety of processes. Deep and elastic scattering, PP bar, PP, inclusive jet production. It does very, very well. So, despite the challenges, we've been able to come a long way with that. And so, let's dig into QCD a little bit. It's just like QED, only different. And how is it different? Well, QED, it's an abelian U1 symmetry. And so here I have an electron, and from freshman physics, the electromagnetic force is 1/r squared. And then, of course, I can polarize the vacuum with E plus E minus pairs. And then if I go to large distances, the force gets weak. Of course, if I go to very small distances, that 1/r starts to blow up and I have issues to deal with. But so if I flip that around, if I talk about energy scales, and that's reciprocal length scales, basically at large energy scales, it's large energy scales, the coupling is large, but at large distances or small energy, it's small. And here's the details, and here's the Lagrangian. In particular, there's zero term here. The field strength tensor is proportional to the A field, but there's no nonlinear terms there. So let's compare that to QCD, and the difference is that there's this non-abelian term. That means the gluon can interact with itself. That wasn't present for the case of the photon. You can't have the photon interacting with itself. The photon is chargeless and it interacts with things with charge. But that is not true with the gluon. And because of that, you can modify, you can have not only quark antiquark loops here, but you can have gluon loops. And the result is instead of screening the color charge, it does the inverse, and it actually makes it larger. So as you go to larger distances, or as you go to larger distances, it actually gets large. So it's the inverse of what we had before. And for example, here's a detailed compilation of the strong coupling constant as a function of the energy, and think of that as 1/length. And you see at low energy scales, it's very large. very difficult to do perturbation theory. But if you work at large energy scales or short distances, then it is reasonable. And in fact, it's about a 10% here. And so the first order correction you expect to be 10%, and second order would be a 1%, et cetera, et cetera. So that's what we're dealing with. So here's sort of a cartoon version. And if you have two quarks, they interact via the color force. And if you try to stretch them, if you keep them close together, it says the QCD force is very weak. And so you can do perturbative expansions and things like this. But if you try to pull them together, there's a very strong force. It's like a rubber band between those two. And as you pull and pull, eventually that will snap and it'll create a quark-antiquark pair. And you'll have two mesons left over instead of a single quark. And so here's a cartoon version. If you take a quark-antiquark pair, you try to pull it apart, eventually it'll snap and create two mesons. And then you can also have a baryon, for example, three quarks like this. And so here's our cartoon version of the proton. And that's what we're working with. So let me restate the problem. So you go to the cafeteria at Brookhaven and you're listening to a couple of theorists arguing. One says, gee, the universe is completely described by the symmetry group SO10. And the other says, you're wrong. The correct answer is supersymmetric flipped SU5 cross U1, whatever that is. And then the other said, no, the only rational choice is E8 cross E8, dictated by superstring theology. And the experimenter comes along and say, enough of this. I will decide it. I'll go make a measurement. We can settle this question once and for all. And the theorist says the problem is you can only predict interactions between fundamental quarks, fundamental particles, and that's quarks and leptons. That's not these complex mesons and hadrons. So, okay, you go down to the EIC and say, great, give me a beam of quarks and leptons. And as the accelerator operators will tell you next week, we have quarks, but they only come in a 3-pack and we can't break a set. So that's the problem. That's what we're working with. We'd like to do fundamental studies of quarks, but we have to deal with them in the form of mesons and protons and nuclei. And so, of course, at RIC, we do gold on gold, and it looks something like that. That's an artist's conception of this. Here's a real diagram. Here's S Phoenix and star. And again, these are very complex objects, and you get hundreds of particles coming out. And the challenge is to decipher that and figure out what the underlying physics is. So that was happening. And in fact, Rick concluded operations earlier this spring. And now we're switching over to the Electron-Ion Collider. So we're going to keep one of the nuclear rings in the RIC facility and then add a separate electron beam. And then we can do electron nuclear collisions. And so this will be the future. And this is the EPIC detector that is being designed and will be used for the EIC. And that's coming along very, very quickly now. And you'll hear more about that later today. So let me start with how do we deal with this proton object? So we're stuck. We have to work with quarks and bags of protons and mesons and nuclei. Because they're confined, that's the minimal unit we can work with. Okay, and the trick is that to get the highest energies, in fact, it's with accelerators involving hadrons. You can do lepton, but typically it's harder to get that up to the very highest energies. For example, the Large Hadron Collider goes up to 14 TeV, but that's proton-proton. And so we better learn how to work with these protons and nuclear objects. And so, they're very complex objects. I mean, here's a, cartoon of the proton, and you have to worry about the QCD interactions, the QED interactions. There's all sorts of things that you'll be hearing about later in this talk, but that's too complex for us. We need to simplify and focus on this a little bit. So, being a physicist, I want to make it as simple as possible. And so here's my simple version of this. I'm just going to pretend that the proton is a bag of a free up-up-down quark. And that's about as simple as we can get. And we're going to make a few other assumptions that get us to the parton model, and I'll talk about those later. So in some sense, this is the old joke that we're working in the limit of a spherical horse, but those are the kind of approximations that we're going to start with so we can make this tractable, and then we'll go back and see how good those approximations are and validate them and try to understand the uncertainties. So that's where we're going with all this. So if I'm going to model the proton as a bag of free point-like quarks, what do you expect for a point-like object? How does that scale? For example, let's suppose this is a point-like object, okay? And I want to observe it, so I shine a photon on there. I shine a photon of this wavelength, and then the cross-section will be something, this is what you need for dimensions, and then it'll be some constant, okay? And then I say, I want more detail. I want to resolve that at a shorter distance, higher energy, so I shine a higher energy photon on that point-like object. And if it's really point-like, it'll still be one, okay? Because it's point-like whether you look at large scale or small scale. And then I really crank up the energy and go really high resolution. And if it's point-like, it'll still be one. So this is a scaling property, and this is reflective of point-like objects, okay? And it was, in part, this was what led us to the quark model that we have now. Now, here's another object, and you can say, is this a point-like particle? Well, you shine a light on it at low wavelength, and you get low resolution. And as you get higher and higher, you start to say, gee, there's some structure there. And you go a little farther, you say, it's not a point-like object at all. It's more complicated. And look at that, we found the Higgs. Well, that's great. So, okay, this resolution didn't come out too well. But again, if you look at, just matter at different scales, if you're studying the KV scale, doing atomic physics, it seems like the atoms are little billiard balls, and that's a good model. But as you up the energy, you find out that there's this hard nucleus in the middle. And if you up the energy some more, you go to the MeV to the JeV scale, then you find that there are the hard things inside the protons. And we've gone up to the TeV scale. And to the extent we've found out so far as we can tell, the quarks are point-like particles. We haven't resolved any structure inside of them. And the electron is a point-like particle. And in part, that's why we're using the Electron-Ion Collider. We're using the point-like simple object to probe the nuclei and the protons to get a handle on that, to make it tractable. So let's come back to the proton. With the proton, if I look at it with low energy, that seems to be a hard billiard ball. If I'm probing that, the MeV characteristic scale. And as I up that, I start to discover there's a bit of structure to that. And then when they did the early deep inelastic scattering experiments at SLAC, as they got up to high energy, they found out that eventually this did become sort of independent of energy and had these factors. And that was the model that we use for the point-like objects. And so at some low scale, it looks point-like. You begin to resolve a structure to it. And then in my simple model, it's just 3 free quarks inside a proton. Of course, we're going to fix that up later, but that's the direction we're going. And this is the historic curve. This shows a selection of data for the structure function of the proton. It could be a function of X and Q. I'll define those in a moment. But the important thing, Q is the energy scale, and that's related to the energy of the photon I'm probing it with. And you see I'm probing it with all sorts of different energies here. And for all these data points, they all seem to lie on the same curve. And what that tells you is this F structure, whatever it is, we haven't defined it yet, it does depend on X, but it doesn't depend on energy. And so it doesn't seem to depend on the energy of the probe. And that's the hint of a point-like object. And that was the data they had that pointed to this parton model, where you say the proton is made up of point-like objects inside of it. Okay. And so let me just pause and recap a little bit so far. So QED is just like QCD is just like QED, only different. And it's that non-abelian feature that makes all the difference and gives us all the headaches, but it gives us all the very interesting structure of QCD that we're going to take advantage of. And the running coupling, that is, the coupling depends on the scale or the energy. That's how interactions change with data. I've skipped over the beta function and some of these things, but I can put these in the separate slides. But the point, the main thing is the scaling and dimensional analysis is very useful, because this is what gives us a clue of we can model the proton in the simple way as to first order a bag of free quarks. So let's try to go a little bit further and characterize the proton. And so the kind of fundamental process we use for that is deeply inelastic scattering, or DIS for short. And so what we're going to do is we're going to take a proton and we're going to shoot a lepton at it, typically an electron, and that will exchange a photon, and then the electron gets scattered out, and it'll break up the proton. And this is somewhat reminiscent of the Rutherford experiment done 100 years ago, where he took alpha particles in a gold foil, and he shot the alpha particles at the gold foil and looked at how they bounce. And what he found was, at the time, they expected that the atom was sort of a blob of electrons with protons kind of scattered around. And when you shoot alpha particles at it, it was this plum pudding. They'd go straight through on average. But what he found was, in fact, that on occasion, some of these alpha particles got reflected back 180 degrees, and that didn't strike at all with this model. And that caused them to revise the model and say, gee, it's got this electron cloud, but in the center, you've got a very hard core where the positive charge is located, and that allowed them to come up with the nuclear model. Here they find a hard center, soft outside. That's the opposite of, example, M&Ms, which have a hard outside and soft center, but that's the history of it. A little bit of terminology. It's deep because the Q squared is very large. Okay, so you're probing deeply into the proton. If you're below a JeV, if you're lower energies, you just see the proton as a billiard ball. And it's inelastic because you're actually breaking up the proton. So that's where the terminology comes from. So let me introduce a couple of the key variables. In this experiment, I'm going to scatter the electron off the proton, and I only look at the outgoing lepton. I'm going to measure the energy and the angle of the outgoing lepton. I don't care what happens here. That's a fully inclusive measurement. You can do semi-inclusive and other things where you measure some of these, you make a charm quark or bottom quark. But the absolute simplest one is you say, I don't care what happens here. I'm only measuring this one. And maybe you've been to a science museum where they have, you shoot little BBs and they have a target that's hidden under a sheet of paper or something like that, and you shoot BBs at it. You try to determine the shape of the target by shooting the BBs. That's sort of what you've got here. You don't see what the target looks like. You only see how the recoil goes. And so I've got 2 degrees of freedom. I've got the energy and the angle of the outgoing lepton, and I can turn those 2 variables into X and Q. Now we're going to get there. Q is that's the energy, basically the energy of the photon that's being exchanged there. And the X, we'll see in a moment, that's a Bjerkane X, but we're going to relate that to the parton momentum of the quarks inside there. Okay, so those 2 variables, I'm only measuring 2 variables, but this mapping gives it to me. A couple of the common variables is nu, the energy difference, and Y is the inelasticity, just scaled by that, or some of the other variables that we'll use there. And so, this diagram represents the amplitude for a lepton scattering with a proton. That's the amplitude. If I want a cross section, I need the squared amplitude. So I take the amplitude complex conjugate multiplied together. So I'll represent the complex conjugate by reflecting it like this. Here's the amplitude. Here's the complex conjugate amplitude. And then the way I'm going to calculate this is I'm going to, all the stuff in blue covers all the leptonic stuff. And all the stuff in green covers the hadronic stuff. And the reason I divide it that way is the leptonic stuff, these are fundamental particles, and I know how to calculate that exactly. So I'm going to call this L mu nu. They only communicate via a photon here to photon here with 4 momentum q mu and 4 momentum q nu. So I can call this big blue blob on top lepton mu nu, and this big green blob on the bottom W mu nu for the hadronic part. Okay, and this leptonic part, I just go to the standard model. I turn the crank, and I find out what that is. It's this part, the hadronic part, that I have a challenge with, because in here is all the non-perturbative physics, all the strong interaction physics of the proton of the nucleus, and that's what I have to deal with. And so the cross section is the amplitude squared, and I can write that as the leptonic part and the hadronic part. And this harkens back to, back in the 60s and such when we talked about, a leptonic current and hadron current interacting and current interactions and things like that. But that's sort of more historical. So that's what I've got so far. And what can I do? What can I do with this object? It's non-perturbative. I can't calculate it from first principles. What can I do? And the answer is, well, I know it's, the tensor structure, it's got a mu and a nu from the two photons that are communicated there. And so what I will do is I will expand this out in terms of all the possible Lorentz structure. And so I've got, it's a rank 2 tensor. I have a G mu nu. I can have a P mu P nu. I can have an antisymmetric PQ. That's going to be a peri-violating term. And we usually stop there. But if you look in detail, there are actually 3 more terms. You can have a W456. The 4 and 5 we usually neglect because there's a proportional to the lepton mass. And so they're typically small. And the 6th one is actually 0 from symmetry. But if you want to know about the 4 and 5, maybe I think Eduardo may give a flash talk later. He's actually calculated those. But we usually stop there because those are the dominant ones. So all I've done is expand this out and said, I have no idea what this is. It's non-perturbative, but I'm just going to write out in the most general Lorentz structure I have. Okay, just no physics, just sort of Lorentz invariance. And the W's are historic. We typically want to compute those to scaling structure functions, so I drop in some factors. And so here's the same thing written in terms of the more modern F structure functions. Okay, and this M here, that's the proton mass if I include that. So no physics. I've just expanded out in terms of Lorentz structure functions. Now I'm going to use a helicity basis, and you'll see why that's handy in a moment. But you can traditionally we do it in terms of F1, 2, 3. F3 is parity violating. F1 and 2 are sort of related through the longitudinal structure function. But here's the mapping between the right, left, and scalar helicity structure functions. Okay, and so it's just the mapping. So I go from here, and here it is. Here it is for the in the helicity basis. Okay. At this point, I've not yet mentioned the parton model at all. Okay, this is all I've done is use Lorentz invariance and just parameterize my ignorance. That's all I've done so far. So. And what's interesting, if you go and measure these structure functions, for example, if you measure F2, and here's a compilation including BCWS a series of data, what you see is as a function of the energy that it's roughly invariant of energy. Okay, at large x and small x, it deviates a little bit, but in the central region, it's invariant of energy. And when you see something that's invariant of energy, that means when I probe it with different wavelengths, it looks the same. That cries out to be, that represents some sort of point-like object. And so that in part was the hints that led people to say, gee, maybe we can describe this as a point-like object. So, there's scaling violations observed at the extreme x value. We'll get to the scaling violations later. But the important thing is that to a good approximation and over a large range of the x, that seems to be independent of energy, which suggests a point-like object. So parton model there. First time I've said parton model. Okay, so we're going to go as simple as I can because, I like to keep it simple. And I'm going to pretend the proton is just a bag of 3 quarks, red, green, and blue. That makes it colorless. And then I'm going to pretend my deep elastic interaction is the lepton comes along, it emits a quark, and it hits one of the quarks in the proton and just flat out knocks it out of the proton. Okay? And what's the probability for seeing quarks in the proton with various properties? I'm going to assume that probability, the parton distribution, I'll call it F, which could be a function of x, which we'll see in a moment is the parton momentum, and q is the energy of the photon I'm hitting it with. It's going to be an up quark and a down quark, and they're going to be 2 up quarks and 1 down quark, and each of them carries 1/3 of the proton momentum. So this delta function means, ensures that the X is a third and X is a third. So I'm going to pretend that, proton has 100% of the momentum, and there's an up, up, down, each carrying 1/3 of momentum. So you've heard of the CTEC PDFs and the MSTW PDFs and the NN PDFs. These are Fred's PDF. You won't find those in OHA PDF for a good reason. We'll see in a moment, but I think they're kind of useful. That's not the whole story, though, because this is a strongly interacting theory, and the QCD comes in, and there are all these gluons tying these things together that make this a balanced system. So the gluons are jumping between these, and you can have gluons making gluon-gluon pairs, and then you can even have them making quark-antiquark pairs, things like that. But the scale that happens at is typically the lambda QCD, which is a few hundred MeV. So how can I get by with this big approximation that I made, where I'm going to pretend that this hits the quark and knocks it out without anything happening? Okay, in particular, we assume it knocks it out so fast that it leaves without this red quark being able to communicate with the rest of it. These are, we're going to argue, are small. Those are higher twist contributions. And how can we make that assumption? Well, if this gets knocked out so fast that it doesn't have time to make a telephone call to the other ones and say, hey, I got hit by an electron, or I got hit by a W boson, or there are things there, and communicate what type of process it's in, because it gets knocked out so fast, it knows nothing about the process, it can't communicate. Then that approximation might work. And so what we need is the time scale of this red quark to be much shorter than the characteristic time scale of what's going on in the proton. And time scales and energy scales are reciprocal. So what that means is, if the time scale of the red one is very large and the time scale of these green gluons is small, that means the inverse of those, that means the scale of the Q is very large compared to the scale of lambda. And so we're going to have corrections of order lambda over Q. Mostly it comes in lambda over Q squared. And so lambda is a few hundred MeV. So that's why if my Q squared is a JeV or more, this is a good approximation. And these sort of things don't happen too much. It gets knocked out so quickly, it doesn't have a chance to telephone back and say, I got hit by a W or a photon or something like that. That's one of the fundamental assumptions of the parton model that allows us to write the cross-section as an independent probability of finding parton A in the proton, and then parton A then participates in whatever hard interaction. And we write that as a convolution, and because when you write as a convolution, that's an independent set of probabilities. And I'll have a homework on the next slide. For example, a coin flip, coin flips are independent no matter what the general public says. And you can write coin flips as a convolution like that. So this is our model. And it works. There are going to be corrections, basically Q squared over lambda squared. But to that approximation, I can say that there's some probability for finding the quark A in the proton. And then this sort of factorizes. What happens in here and happens in here are independent. They only communicate by that parton A. So this is the general framework. And let's step back, and how do we do this? So where do we get this from? Because this contains all the non-perturbative information about what's going on in the proton. Well, this hard scattering process, that's something typically I can calculate. So it involves a fundamental photon with a fundamental quark, fundamental particles. I have a standard model for that. I can calculate that hard scattering cross-section in the standard model. This object I can go and measure. So I can get this from experiment, and I can calculate this. If I know this, I know this, I can invert the problem and get this. And that's, in fact, what Pavel will be talking about on Thursday and Friday. And again, the corrections are ordered lambda squared over Q squared, because those are roughly the energy scales or the time scales of what's going on. Okay. And now let me write down a model for this. Okay. In the parton model, we say the proton is made up of quarks and antiquarks, and there could be scalar quarks. We don't know. Let's put it in and see what happens. Okay. And because I know they're up quarks, they're down quarks, there may be other things. We'll wait and see. But that's the model for it. Okay. And here's the homework. For convolutions, you usually see the convolutions written this way. When I write it this way, it's not clear that it's symmetric with respect to f and g. It seems like there's sort of a special thing here. But if you slip in the delta function, that makes it explicit. And it's actually sometimes useful when proving factorization theorems. The other homework is show that convolutions are a natural way to multiply probabilities. So for example, this represents the coin flip. There's a half probability. It comes up heads +1, half tails -1. And if you convolute that together, you get 2 coin flips. And because they're independent, you can write it as a convolution. This has a plus here that has a times here. You can actually map the two with an exponential function if you want, but I'll leave that for homework. All right, so at this point, to get to that formula, I only use Lorentz invariance and no parton model. And this was my parton model, where I assumed that the proton was made up of a simple combination of quarks, antiquarks, and maybe it could be a scalar. Okay, and I've written it in the helicity form because that's particularly nice because they come in very simply, as you see in a moment. And so this is my parton model, and this is just Lorentz invariance. And now what I can do is I can line these up. I can go and measure these things from interactions. And what I see in particular, I see that the antiquarks are going to be proportional to 1 minus y squared term. The scalar quarks are being proportional to 1 minus y, and the quarks are constant. And so I can line these up, and it works very nicely. And so if I go and measure these f's, I can figure out what these are. Okay, and I've done this for neutrino scattering. The alignment is particularly nice there because neutrino scattering, it exchanges a W boson. That's a left-handed weak interaction. And so what you see is that the quarks line up with the left-handed structure function, the antiquarks line up with the right-handed structure function, and the scalar quarks line up with the scalar structure function. If you do photons, then you have both left and right, and you have to decompose that. But that's why I use helicity. But it works just fine if you use the 1, 2, 3 basis too. And so that's how we make the association. And again, here's the relationship between the two. So when we go and do this, what we find is we find there are quarks in there, there are antiquarks in there, and we look for scalars in there, but we find out there are no scalars. Okay, and so what it means is there are no scalars, and that means the scalar structure function is 0. Now let's look on the relation here, and here's the scalar structure function. If this is 0, that means there's a relationship between f1 and f2. And the relationship is f2 equals 2x f1. And that's called the Kelvin-Gross relationship. And at least when I was in grad school, they said, here's the Kelvin-Gross relationship, and that means that there are no scalar quarks. And I said, how does that connect? And in the F1, 2, 3 basis, it's not so clear. But if you switch to the scalar basis, you just see if there's no scalar structure function, there are no scalar quarks. Okay, so that's the relation. That's observed, and that's what led us to say, they're quarks, they're antiquarks, but as far as we can tell, there are no scalar quarks. Okay. Now, let me go into a little bit more detail about the longitudinal structure function, because I'm working at leading order, but at Hera, they've measured this very accurately. And the longitudinal structure function is special. And the longitudinal structure function is related to the scalar with the factor here, but it's not completely 0. Okay, and if you work it out, there are corrections. First of all, at leading order, there's a mass term, because basically it's 0 because of helicity arguments, but mass terms can violate helicity arguments. If you have a mass, you can boost to a frame where the thing's going in the opposite direction. The momentum flips, but the spin doesn't. It'll flip helicity. And so there are corrections proportional to the quark mass. But also when you go to higher orders, there are corrections at higher orders, and that's where the gluon comes in. And these are very interesting because the longitudinal structure function has been measured, and that gives you a handle on the gluon rather directly. And so here's, that's not the best. Sorry, I should have pulled up. There's a more updated plot on this. But here's some preliminary results from FH1 on the FL, and that gives us information on, mainly the gluon distribution. Okay, so let's come back to our toy PDFs. Okay. All right. And so here's my toy PDF. First thing I want to emphasize is it's perfectly scaling. Okay. Here's the U quark distribution as a function of the parton momentum fraction and the parton energy, and it does not depend on energy. It looks this way whether you look at it with a long wavelength or short wavelength probe. Okay, so it's Q independent, perfectly scaling. Wonderful. Okay, let's check the quark number sum rule. If I integrate over the quark probability function over all possible momentum going from 0 to 1, if I work it out, I find out there are 2 up quarks, 1 down quark, and 0 strange. So that checks. All is good. All right, very nice. Let's check the momentum fraction. So if I drop it in X here, I take the probability times the momentum, and if I integrate over, I get the total momentum carried by the quark flavor, and I find out the up quark is carrying 2/3 of the parton momentum, or the proton momentum, and the down quark is carrying 1/3 of the proton momentum. And you add those up, and it works. The quarks are carrying all the proton momentum. So everything seems nice and happy. Why is this out on OHA PDF? Well, the next thing you do is you actually go and do those measurements. You get the structure functions, and then you work out the structure function. You put them in here, and you check the momentum sum rule, and you don't get 100%, you get 50%. So something's going on. You add up all the momentum of the quarks and antiquarks, and it only adds up to 50% of the proton. What happened? Okay, I lost half the proton momentum somewhere. What's going on? Well, this was one of the controversies they faced when they did the SLAC DIS experiments, and eventually they figured out the solution is there are gluons in there. Okay, there are gluons in there, and the gluons, in fact, carry about half the momentum of the proton. But because they don't couple to the photons, you're not probing them when you're probing them with the photons, and so you're missing out on those. And so by doing this measurement, they were able to indirectly determine that it wasn't just the up and down quarks. They figured out there weren't scalar quarks because of the Coulomb-Gross, but there must be something else in there, and that was hypothesized that was the gluons that is holding all this together. And so now let's take those simple Fred PDFs that I had, okay, and add in the gluons. And so we need the gluons to kind of hold things together. So here were my parton distributions before. It was just a delta function at 1/3, okay, each of the 3 quarks had 1/3 of the proton momentum. And when I put the gluons in, that's going to smear things out. So I take that delta function and I smear it out. Okay, I smear it out like this. And in particular, it turns out there are lots and lots of quark-antiquark pairs at small momentum fraction, at small energy. That's because the strong interaction gets large at small energy. And so it gets large at small energy. It means alpha S is very large. It's very easy for a gluon to split into a very low energy quark-antiquark pair. And so it turns out you can make an infinite number of quark-antiquark pairs at small x. Okay, so let's go back to our sum rules and check our sum rules now. Because before, when we did the sum rule, I found out there was 2 up quarks and 1 down quark in the proton. But now, because the gluons can split into an infinite number of these, if I do that again, I'll get infinity. And in fact, the quark distributions diverge like 1/1 to the 1/x to the 1.5 or so, something like that. So what do? Well, the answer is I take the number of quarks minus the number of antiquarks, okay? Because in this process, anytime I make an up quark, I also make a down antiquark. So this process will always conserve U minus U bar, and this will be infinite. This will be infinite, but the difference will be 2. And then same for D. D minus D bar will give me 1, and S minus S bar had better give me 0. So the solution is I have an infinite number at small momentum fraction. Saturation is another story. But because they're pair produced, if I do this difference, then that's the momentum sum rule, or the number sum rule that I impose. Okay, so let's take a look at some real PDFs. Okay, and so here are some real PDFs. Here's the U valence, the D valence, and then I can have U bar, D bar, strange, charm, gluon. And the gluon, to fit the gluon in there, I have to divide that by 10. Because again, the gluon's carrying half of the momentum fraction, the up is carrying about 30%, the down's carrying about 15%, and there's 5 or 10% spread among the others. One thing you notice is that the valence distributions, and actually these are there's a factor of X thrown in there, but these distributions have a peak not too far from 1/3. That's because primordially, you think at some low scale, the proton was, just 3 valence quarks up, down. So these quarks will have a peak, but everything else is generated perturbatively from gluon splitting, and that means they're monotonically increasing. Okay, and so this is what it looks like at low energy, 10 Jeff squared, but then I crank it up to 10 to the fourth Jeff squared, or 100, and you see they're different. Okay, and so they do change with energy. And so there are scaling violations. They're an essential feature of perturbative QCD. They're there, but they change slowly, as we saw back on the overall figure. And again, where do they come from? So in the XQ space, as I said, you calculate this from the standard model, you measure this from experiment and extract this, and you have to use a variety of experiments. Here's the LHC, many things going here, TT bar, JETS, WZ, Drawley-Yan, BB bar, J psi. Here are the Hera measurements, the Tevatron measurements, fixed target measurements, and then EIC will be in this region. And by using all these together, we can then figure out what those party distributions are. So here's homework and some sum rules. So you can just check, but for example, if I look at the structure function F2, if I probe the proton with the photon, then you see the up quark, which has charge 2/3, it's just the charge squared. These things have charge 2/3, these things have charge 1/3. When you probe it with the photon, you're basically getting a charge average combination. Whereas the neutrino processes are quite useful because that's the weak interaction, and that gives you different combinations. So you see here, if I do neutrino, antineutrino, I have something different. And then I have F2, which is parity conserving, F3, which is parity non-conserving. And so in neutrino processes, I have 4 linear combinations of PDFs, whereas in photon case, I only have 1. And that's why the neutrino DIS are so important. But the problem with that is neutrinos don't have a big cross-section. The Earth is essentially transparent to neutrinos. So in those experiments, we have to use very dense targets like iron and lead, but then you have to get to the nuclear corrections, which I'll talk about tomorrow. Anyway, so you can take a look and see if all that works out. The other one is using those relations, you can check some of these sum rules. And before we had a parton model, these sum rules were developed back in the current days, and they found these particular relations. But if you sort of use that parton model as I laid out, you should be able to verify those at the simple order. So I'll leave that in the notes. One last topic I want to talk about is evolution. What does the proton look like at different scales? And I just showed you in that previous plot, Q squared of 100, Q squared of 10 to the fourth. They look different. Where does that come from? Okay, and so the answer you get depends on the question. And so I took this from an old preprint by Charles Dodgson some time ago. I don't think it's on archive, but so this is Alice, one of the investigators, and the Cheshire Puss. And she says, Cheshire Puss, would you please tell me which way I ought to go from here? And he says, that depends a good deal on where you want to get to, said the cat. I don't much care where, said Alice. Then it doesn't matter which way you go, said the cat. Oh, as long as I get somewhere, Alice explained as an explanation. Oh, you're sure to do that, said the cat, if only you walk long enough. So it's important to make sure you define your question properly. Otherwise, the answer could be ambiguous. And when you ask what's inside the proton, you need to say at what scale, because the proton looks different at all different scales. Okay, if you probe it at very low energy, long wavelength, it looks like a hard billiard ball. And you can do atomic and nuclear physics with that. But as you get up in higher energy, like high energy nuclear physics, then it looks different. And we can take advantage of the uncertainty principle. I can cheat on the energy conservation, but if I do it, I have to do it for a short amount of time. Okay, so I can create in the proton weighs a JeV, the top quark weighs 175 JeV. So you say, there's no way I could have a top antiquark pair inside the proton because I put it in a scale, it weighs 1 GeV, and a top antiquark pair would weigh twice times 175. It doesn't work. But because the Heisenberg uncertainty principle, I can do that for a short amount of time. And if it's short enough, the quantum police won't know, and I can get away with it. And so this is what's going on. I've got my primordial up, up, down, okay? And then I can make a top antitop pair, and that exists only for a short amount of time. So if I assume everything moves at the speed of light, that can only go so far before the quantum police say, up, time's up, you better go back. And the bottom weighs 5 GeV, so that'll go a little farther. The top weighs the charm weighs 1.5. Strange is about a half, and then these are very light, the gluon's massless. So if I look at different scales, I will see different things. If I look at fairly low scales, I'll see lots and lots of gluons, and then I probe a little more, I'll see up and up U and U bar pairs, D, D bar. And if I probe closely enough, I'll see B and B bar pairs inside the proton, and even T and T bar. It's possible. It's all allowed by the uncertainty principle. And so when I do my calculation, something a little detail I left out is, here's my process. The electron comes in, emits a boson, and then it strikes this red quark. And I have to decide where I draw the line. When I factorize this into a hard scattering and a hard-time distribution, I have to decide where am I going to draw the line. Am I going to draw the line here and say, this is a hard scattering, this is a PDF, or I could use a medium scale and say, this is, and if I change different scales, this will change, but this will change also. Okay, so there is a very weak dependence on the energy scale. And so there is a very weak dependence on my PDF. So how does the PDF change with the scale mu? Because if I move this back and forth, if I probe the PDF at different scales, I'll see different things. And if I probe at really, really high energy, really small scales, I could even see top and top pairs coming out of the proton. So let's take a look at that. So here's my one-page quick and dirty renormalization group equation. Okay, and so here's the parton model. The experimental physical cross-section is the parton distribution convoluted by the hard scattering cross-section. And I'm going to use, we sometimes use sigma hat here for that, but that hat gets lost a lot. I'm going to use omega for my hard scattering cross-section, especially because I'm going to drop in some tildes. And technically, I have to take a Mellon transform to separate the convolution. That's homework in the next page. But let me be fast and loose with the calculus. So what I'm going to do is I'm going to take a derivative of the parton model. And so I ask, how does the experimental cross-section change with this mu factor that is the boundary line between the parton distribution and the hard scattering cross-section? Well, that's a physical observable. And the mu is just the convenience for allowing me to calculate. That's where I arbitrarily draw the line between the two objects. So that physical cross-section had better not depend on that arbitrary theoretical construct. So that derivative had better be zero. That is the renormalization group equation. Okay, it says it should not depend on that renormalization scale. And now I'm just going to apply the chain rule. I have df omega and fd omega. Okay, and that's what I have. And now when you see something like this, you say, gee whiz, I'm going to group all the F stuff on one side and all the omega stuff on the other side. And you've seen this before. What do? You say, I'm going to do separation of variables. Okay, I'm going to do separation of variables, and I'll just put in a separation constant, minor lambda. And now I can solve both of these. I can solve, I have a differential equation for F here like this. But let me back up one step. When I write it like this, these F's include all that non-perturbative, ugly, strong interaction stuff we can't calculate. This is non-perturbative. On the right-hand side, this is the hard scattering cross-section. I get that from the standard model. That I can calculate. And what's remarkable about this equation is I can calculate this. I can't calculate this, but they're related. So because I can calculate this, I can get gamma. And because I get gamma, I can solve this. This gamma tells me how F changes with energy scale. Okay, it tells me how F changes with energy scale. And you notice there's a log here, because there's a log here, it changes slowly. And you see on the plot I showed before, the scaling wasn't perfect, but on a log scale, it changed very slowly. And so that's where it comes from. And now I can solve this in Mellon space. That's what the tildes mean. And if I solve this, I find out the dependence of F on mu is the Parton distributions. It's mu to the minus gamma. Okay. And gamma is what we call the anomalous dimension. Where does that mystery term come? It's historical, but it's a dimension because it's the mass dimension of this solution. And it's anomalous because if F satisfied perfect scaling, that is, if F did not depend on energy scale, gamma would be 0. Okay. And so this anomalous dimension tells me how the scaling is violated. And this is what it is in Mellon space. If I convert back to X space, I get the convolution back. And so F changes logarithmically with the scale by some splitting function times F. Okay. This is the DGLAP equation. That tells us how the Parton distributions evolve in scale. And what's nice about this is if you go to experiment and find the X dependence, I don't need to do the Q dependence because I can do that right here using the normalization group equation. And Pavel will talk more. Homework in the Mellon transform, try it out. When you show this factorizes, it's nice to use a delta function of the delta function form of the convolution. It makes it a whole lot easier. So let me just show you some examples. Again, if the mu, this mu renormalization scale tells me where I draw the line between what's the hard scattering and what's the PDF. And so here's how the up quark changes going from low scale to high scale, and changes very slowly. And then here are the details. And let me just show a few more. Here's how the up and down change. Here's how the gluon and the strain change. And again, the valence, they have the bump here because they in my simple picture, they started out with all momentum fraction of a third, but the things that are radiated like gluon and strain are monotonic. And then one other figure that's kind of interesting, if you look at the momentum fraction versus energy, when you go down to very, very low energies, the proton is basically half gluon and then it's up down. It's got a little bit of U bar, D bar, and strange. Those are very light quarks. But initially, it doesn't have any charm or bottom. And then if you probe it at a little bit larger energy, you start to see CCURs pair popping up. Initially, they're not many, but then they kind of come up. And then eventually the bottom comes on. And I don't have it here, but in principle, the top could come on too. And in fact, as I go out to higher and higher energies, you see here the D bar, U bar, and S bar are almost the same. It's almost like there's an SU3 symmetry. And in principle, if I went out to infinite energies, I'd have an SU3, 4, 5, 6 symmetry. But you can see how they actually come on as a function of energy. So that's a nice snapshot to give you a view of what's going on over the full range. So there are lots of slides in here, but I'll just leave this as homework. If you want, we can talk about these over the break this evening. Some details and symmetries and things on the splitting functions. And so this is just a recap, but I'll just finish here. And hopefully I've given you an intuitive sense about what's going on behind the Parton model, where this comes from. And then we'll talk about how we apply this to the IC. And then in Pavel's lecture, she shows you how we'll do that to actually 3-loop order for the proton. So I will finish there. And I think unless I'll take any urgent questions, but tonight at 7:30, we'll have an informal Q&A session. So if there are any urgent questions now, otherwise we'll just wait for that. Okay, thank you.
Thank you.